Hello, I wanted to give you some background to help you with the analysis of your lab. In this laboratory, you're going to be exposed to some of the principles of thermodynamics. They're typically called the laws of thermodynamics. The zeroth law says that objects in equilibrium are at the same temperature. So for example, you've got an object on the left at temperature T1, an object on the right at object temperature T2. If T1 is greater than T2, then the heat flows from T1 to T2. That's the direction of heat flow. This is a result of the second law of thermodynamics, which says that heat cannot flow uphill. So heat always flows downhill from high temperature to low temperature. So for example, if it was the other way around and T1 was less than T2, if T1 is less than T2, then we would find that the heat flows the other way. So this makes perfect sense and is consistent with our experience. So we're going to apply the same principle in the laboratory. First question you want to ask, what is the initial temperature of the three objects? I'll give you three objects which were one made of wood, one made of metal, and the other was an ice cube. So you had three different objects. They came from a refrigerator, from a freezer. What was their initial temperature? What is the final temperature of the three objects? Now, those objects were in contact with liquid water. Your liquid water was acting as your calorimeter. So it made it easy to measure the temperature. It wasn't so easy to measure the temperature of the object, but by putting the thermometer and measuring it on a gauge, you were able to tell what happened to the water temperature. The first law of thermodynamics essentially says there's conservation of energy. That means energy is neither created nor destroyed unless you're in a nuclear reactor. So for most common applications, the change in the internal energy, we write that as delta U, delta is the symbol for change, is equal to the heat that flows into your object and the work done by your system. In your particular case, there was no heat and no work. You just had some liquid water, took an object, and you dropped it here. So there's no heat transferred. We'll assume that very little heat is transferred to the surroundings and no work was done. So in our case, delta U is 0 and U is the internal energy. That means if I define my system to include the object and the water, this is my system, its total energy cannot change. So here's how we're going to do the analysis. We drop this object into the water and then we watch the temperature change. The heat gained was equal to the heat lost. Now who lost the heat and who gained the heat? Obviously, if the object was colder, the heat will flow to the object. If the object was hotter, the heat would flow to the water. So you might want to ask the question, who lost and who gained? And then the question is, how much? You lost some heat, you some heat. Well, we're going to get that from our plot of temperature as a function of time. So we asked you to record the temperature, and then you made measurements. And typically you plot your measurements as dots. I've shown a smooth line to indicate how it might go. We say we've reached equilibrium when the temperature doesn't change very much. It reaches its final equilibrium state. Now, if you wait long enough, it might start transferring some heat to the surrounding. The equation that we use to find out the heat transferred is Q equals mCp delta T. Delta T is the temperature from the initial to the final. So this is your delta T of the water. And likewise, you didn't measure the temperature of the object that you dropped in, so you might have to make some assumptions about what is going to happen to its temperature. So this is how we'll know the total heat transferred. We'll make the assumption that there is no heat lost because you started with the water at ambient or room temperature. So it was at ambient temperature, so no reason to expect much heat is lost. You drop the object, and then over time it reached equilibrium. So this is your basic experiment in calorimetry. Calorimetry is the science of measurements of heat. And in your report, you'd like to determine how much heat was transferred to or from each object. So it's either to or from. It all depends. Which was hot and which was cold. So how much heat was transferred? And then the next part of your question is, which of those three objects was most effective at doing this? And ultimately, your goal is to design a thermal tote. So does this experiment give you any ideas on what kind of object might be most effective at giving you the cooling effect that you desire? Hope this helps, and we'll meet in class to talk some more about this.